We're going to take a look at another Calc 2 topic. This is video lecture number 2 over chapter 8 called Integration by Parts. Integration by parts is used when we have the integral of two functions being multiplied by each other. So one of the functions, in this case f of x, we need to be able to differentiate repeatedly, and the other one, g of x, we need to be able to integrate repeatedly. We're going to take a trip back to Calc 1 for just a second, and we're going to look at the product rule. So if we were to take the derivative of f of x times g of x, we would use the product rule, right? Two functions being multiplied. So that would be the first times derivative of the second plus the second function times derivative of the first. And then the opposite of taking the derivative would be the antiderivative or the integral. So if we integrate both sides, then we're just left with an f of x, g of x on the right, on the left. And then we have the integral of f of x, g prime of x, plus g of x, f prime of x, dx. Okay, I'm going to split the right side into two separate integrals. So I'm going to have the integral of f of x, g prime of x dx, plus the integral of g of x, f prime of x dx. And I'm going to solve for this guy right here. So integral of f of x, g prime of x dx is going to be equal to f of x, g of x minus the integral of g of x, f prime of x. And if we let u equal f of x and v equal g of x, then we're going to get a formula that we use for integration by parts. So if u and v are functions of x and have continuous derivatives, then the integral of u dv is equal to u times v minus the integral of v du. That is your integration by parts formula. When we do this, your goal is to try to get something easier to integrate in the v du spot. And to help us out, we have an acronym, LIATE, that we use to determine what our u is going to be and what our dv is going to be. So LIATE stands for logarithmic inverse trig, algebraic, trig, and exponential. We let u equal the first from this list that appears in the problem. And this will make more sense when we start doing some examples. But I always go back to this acronym when I'm deciding what to choose for U and what to choose for DV. So first example, we have the integral of x squared times cosine x dx. Using Lyautey, the first thing I see from that list is an algebraic, the x squared. So I'm going to let u equal x squared. That means my dv is equal to the cosine x dx. And you need a du and a v. To go from u to du, you just take the derivative. So 2x dx. And to go from dv to v, you take the antiderivative. So antiderivative of cosine is sine. And our part is u times v minus the integral of v du. So we're going to have u times v x squared sine x minus the integral of 2x sine x dx. I can pull a 2 out in front. Now we have another problem. We don't know the antiderivative of x sine x dx. So we use parts again. So my u is going to be x, du is dx, dv is sine x dx, and v would be negative cosine x. U times v minus the integral of v du. So we're going to have our x squared sine x minus 2, and that's going to be multiplied by u times v, so negative x cosine x minus the integral of v du, which is just negative cosine x dx. we'll have x squared sine x plus 2x cosine x plus the integral of cosine x dx. Actually, it's going to be plus 2 because I need to distribute the 2. Antiderivative cosine. And this is actually going to be negative. Okay, so these two make a positive, and then we distribute this negative 2, so it becomes negative again. Antiderivative cosine is sine. So we're going to have x squared sine x plus 2x cosine x minus 2 sine x plus c. So there are times you have to do integration by parts more than once. Okay, our next example is the integral of x divided by square root of 6x plus 1 dx. Before I do anything, I'm going to rewrite this where it's two functions multiplied together. So x times, this would be 6x plus 1 to the negative 1/2 power dx. Algebraic comes first, which is that x. So u is equal to x. Du would just be dx. dv is that 6x plus 1 to the negative 1/2 dx. And the antiderivative of that. So off to the side, if you want, you could say, if you're trying to take the integral of that, you could say u is equal to 6x plus 1 du is equal to 6 dx, or 1/6 du is equal to dx. So it's like you have 1/6 u to the negative 1/2 du. Add 1 and divide by that power. You get 1/6 times 2 u to the 1/2, or your v becomes 1/6 times 2 is 1/3, u to the 1/2. Well, u is 6x plus 1, and it's to the 1/2 power. So if you need to do scratch work on the side, that is totally fine. Okay, then we have u times v minus the integral of v du. So u times v is going to give you 1/3 x times 6x plus 1 to the 1/2 power minus the integral of v du, which is 1/3 6x plus 1 to the 1/2 power dx. Now, if 1/3 x, I'm going to rewrite this as the radical. We can pull out the 1/3 and just have the integral of 6x plus 1 to the 1/2. Okay, this is not two functions multiplied. This we can use a u sub. U would be equal to 6x plus 1. Du is 6 dx. We don't have a 6, so divide by that. 1/6 du is equal to dx. So we have like 1/6 u to the 1/2, or 1/6 times 2/3 u to the 3/2. So we're gonna have 1/3 x square root 6x plus 1 minus 1/3 times 1/6 times 2/3 u to the 3/2, but our u is 6x plus 1 to the 3/2 plus c. Then we can multiply and clean up just a little bit. So we'll have 1/3 x radical 6x plus 1 minus 1/27 when you multiply. And that would be your final solution. Okay, our next example. It's kind of a long one. When you see types of problems that look like this, mostly it's an exponential raised to a power with a trig function like this. These are what I call them boomerang problems, because we're going to circle back to have the original integral that we started with. It's going to end back up in our problem when we do our integration by parts. And then we have to treat that as a variable and solve for it. So let's just start by identifying our u and our dv. So using that Liate, the first thing in this problem that's in the list is a trig function. Trig comes before exponential. So my u is going to be cosine 2x. My dv is going to be e to the 4x dx. So du is going to be -2 sine 2x. And our v is going to be 1/4 e to the 4x. Then we can apply our formula. U times v minus the integral of v du. Okay, u times v is going to be 1/4 e to the 4x cosine 2x minus the integral of v du 1/4 times -2 is -1/2. Take that out to the front of the integral, times that negative out in front, we're going to have +1/2. So I'm going to have 1/4 e to the 4x cosine 2x plus, we're going to have a 1/2 out in front, and then we have e to the 4x sine 2x dx. Okay, we have another exponential times a trig function in the integral. So we need to do parts again. U is going to be equal to sine 2x. Du would be 2 cosine 2x dx. dv is e to the 4x dx, and v is still 1/4 e to the 4x. Then we do our u times v minus the integral of v du. So we're going to have 1/4 e to the 4x cosine 2x plus 1/2 times 1/4 e to the 4x sine 2x, right? Because that's our u times v, minus the integral of v du. So 1/4 e to the 4x times 2 cosine 2x dx. Okay, I'm going to have 1/2 times 1/4 is going to be 1/8 e to the 4x sine 2x. Okay, and then I have this times this. 2 times a fourth is a half. Pull that out, so we'll have -1/2 times the 1/2 on the outside. I'm going to have minus 1/4 integral e to the 4x cosine 2x dx. Okay. And then look what we have here. Our original problem, integral of e to the 4x cosine 2x, appears right here. When your original integral appears in the problem, we're going to let this equal I. This is just gonna be like a variable. So the whole process we're doing, the integration by parts, that whole integral is equal to the process we're doing, correct? So we're gonna have the integral of e to the 4x cosine 2x. Actually, I said let that equal I. So our original integral equals I. So I is equal to, it's going to be all of the work we have done but now we're saying our original integral is equal to I. So it's going to be minus 1/4 times I. Then we are going to solve for I. So we're done doing the integration by parts because we're just going to keep cycling back between the e to the 4x sine 2x and then our original integral. So to solve for I, we add 1/4. So we're going to have 5/4 I is equal to 1/4 e to the 4x cosine 2x plus 1/8 e to the 4x sine 2x. And to get I by itself, we divide by 5/4 or multiply by 4/5. So I is equal to 4/5 times, just copying down what we just wrote. And then I is that integral, so the integral of e to the 4x cosine 2x dx is equal to, it's going to be 1/5 e to the 4x cosine 2x plus 1/10 e to the 4x sine 2x plus c. And that would be your final solution for that one. Okay, and then we have one last example. This is not necessarily two things multiplied together, but we can still use integration by parts. So the only thing in this problem is a logarithmic. So we let u be the natural log of 4 plus x squared du would be 2x divided by 4 plus x squared dx. dv is just dx, and v would be x. So we have u times v minus the integral of v du. So natural log 4 plus x squared times x minus the integral from 0 to 1 of v du, which is going to give me 2x squared over 4 plus x squared dx. Okay, we can't do u sub on that integral, but what we can do is take this and do long division. So x squared plus 4. Then we'll have 2x squared plus 0x plus 0. Two x squared divided by x squared is just 2. So we'll have 2x squared minus 8. So we have negative 8. That's the remainder. So we're going to have natural log 4 plus x squared times x evaluated from 0 to 1 minus the integral from 0 to 1. And that long division we can rewrite as 2 minus 8 over x squared plus 4 dx. Okay, we can take the antiderivative of 2. And then this portion right here should ring a bell as arctangent, where u is equal to x, a is equal to 2, and the integral of du over a squared plus u squared is equal to 1 over a arctan u over a plus c. So we're going to have natural log 4 plus x squared times x minus 2x plus 8 times 1/2 arctangent of x over 2, and all of that's evaluated from 0 to 1. So we have natural log, we'll have 5 minus 2 plus 4 arctan of 1/2 minus 4 arctangent of 0. And this is going to simplify to natural log of 5 minus 2 plus 4 arctan of 1/2. And then if you want, you can put that in the calculator to get a decimal, but that would be your final answer. And then there is a really quick method that we're going to talk about real quick. The last thing is called the tabular method. It works well for integrals in the forms given right here. And how it works is you make a table. The first column is going to be called sine. Then you make a column for your u. And then you make a column for your dv. So the sign is always going to alternate between plus and minus. And your u, you choose the same way as you normally would. So u is going to be our algebraic, because that comes before exponential. And dv becomes e to the negative 2x. So going down for your u's, you take the derivative. So we'll have 3x squared, 6x, 6, and 0. You go all the way till you get to 0. For the dv column, we take the antiderivative. So we're going to have negative 1/2 e to the negative 2x. We'll have 1/4 e to the negative 2x. Negative 1/8 e to the negative 2x. And 1/16 e to the negative 2x. Okay, then you start with the positive, and you're going to multiply straight across and diagonal. Multiply straight across and diagonal. Straight across, diagonal, straight across, diagonal. So we're going to have negative 1/2 x cubed e to the negative 2x minus 3/4 x squared e to the negative 2x minus 3/4 x e to the negative 2x minus 3/8 e to the negative 2x plus c, and then you are finished. It's literally that simple. Okay, that is all for section 8.2, integration by parts.